और सुनो, वो जो रॉ वीडियोस रिकॉर्ड हुई है ना,
हाँ
वो कहीं पे अपलोड करके मुझे भेज दो, मैं ट्विच पे अकाउंट बना करके उधर डालना चालू कर देता हूँ। और
ठीक है।
जितना कोड इकट्ठा हुआ है वो मैं प्रॉपर उसको मतलब झाड़ू पोछा मार करके थोड़ा ठीक ठाक करके उसको मैं उस पर गिटलैब पे डाल देता हूँ। तो वो इंडिविजुअल एक एक चिप डाउनलोड करने की बजाय बंदा सीधा जो है एक ही रिपोजिटरी से वापस पूरा पुल कर सकता है।
हाँ वो भी कर सकते हैं। नहीं ऑलरेडी मेरे गिटहब
ऐसा
अपलोड है।
नहीं,
हाँ
नहीं, उसमें एक फायदा और है ना कि मैंने मान लो बाद में कोड में कुछ फिक्स किया
हाँ हाँ
तो
अब
उसमें फिर उनको डायरेक्ट उसका हिस्ट्री में दिखेगा
हाँ
कि
हाँ
उसमें कुछ कोड में चेंज हुआ है।
हाँ हाँ चलो वही करते हैं ना फिर।
हाँ ठीक है, वो मेरे पास गिटलैब रखा हुआ है, मैं करके देता हूँ थोड़े दिन में।
ठीक है तो चलो मैं रिकॉर्डिंग स्टार्ट कर दिया।
ठीक है।
मैं जाता है, ध्वनि दीदी आगे कंट्रोल करेगी।
ठीक है ठीक है। Guys, we are waiting for a couple of minutes more and then we will start at 6:05 p.m. Okay guys, we are starting. Let me share my screen. Okay, is my screen visible to everyone? Hello.
Yeah, screen is visible.
Okay, great. So till last session, I think we covered our RAT completely, and we covered bunch of techniques on anti-debugging. So I will take a quick recap of anti-debugging techniques. So these are the techniques which allow us to basically detect debugging. They allow us to prevent debugging, and in certain cases they allow us to evade from debugging. Again, there is a little bit of difference. This will first one will only help us in telling us whether we are under debugger or not, and second one will simply block debugger from attaching to us, and third one will help us in getting out of grip of debugger. So, for example, if a debugger is trying to halt execution at some particular place and try to inspect what is going on, there are techniques which allow us to uh, continue execution even if it is a debugger that is trying to break there. So we will cover them one by one. Detecting debugging is pretty easy part actually. So here we have two major techniques. One is timing analysis that we covered in previous session. The basic concept is that code under debugger takes more time than out of it. Then we have process detection. So we basically detect our parent process and check if it is a known debugger. Now, for preventing debugging, there is a common technique that uses ptrace, and first one is to use simple ptrace call to attach to self. But the drawback is that this can be bypassed using LD preload. So what we do that we improve this technique and we chain ptrace calls with internal state. So here to evade it, the analyst has to reverse engineer the internal state and try to maintain it. So we will start from chaining ptrace calls. For example, this is the timing analysis code that we covered last time. Okay. This is the simple ptrace to self that we went through last time. With LD preload, it is possible to sort of spoof this particular call. So the process that we are trying to debug cannot detect whether it is in the debugger or not. So as an improvement, what we do that we chain it. So first one should succeed, and subsequent ones are going to fail anyway because this one succeeded. So here what we do that we do some simple operation here and try to save output somewhere else, and here we check the output. So if both these calls go through, for example this and this is executed, only then this particular condition will match. And if suppose this particular call fails, as in something else has already attached to our process, so this particular instruction will not be executed, and eventually this check will fail. So here if we are even able to do this, try to bypass this, we have to take care of this internal state. And still there are ways to figure out using LD preload, but then again you have to check which error conditions are getting triggered where to ensure that you are returning same value in and exactly same order so that our internal state is maintained correctly. So if we want to check how this works, so wait, here is the process ptrace2. This says normal execution, and if we do gdbq and we try to run it, it basically goes somewhere else saying don't trace me because internal state does not match anymore. Similarly, if I attach strace or something, even then it will exit with this don't trace me line. Same is going to happen if I attach something called ltrace, even then it will exit. So this is one way to figure it out. And now, as I told you here, it is possible to evade it by reversing this internal state and trying to maintain it while we are going through bunch of these chained ptrace calls. There is yet another technique that is even harder to evade, and that is called having an invalid state without debugger. So here idea is very simple. The idea is that process uh, will fork, then parent will attach to child as debugger, then child will trigger illegal syscall or some other instruction if you want. Here parent process gets the signal, then parent process fixes the code and child resumes normal operation. Now here the problem is that if I am acting as an analyst and I want to figure out this particular code, so here parent has to attach to child as a debugger to fix the code, but the parent cannot do that anymore. So the thing is that this illegal syscall will not be fixed and child process will basically crash. So if I want to detect it and basically prevent it from happening, then I have to figure out this code fixing part, how it is happening, where it is happening, and then I have to do all that part manually to ensure that code works as intended. So the code looks something like this. Here I have defined a custom syscall number that actually doesn't exist, and here I am calling that syscall using syscall function from glibc. And here what I have done, that I have only changed the order of parameters. So in the fixing part, I only have to swap the order and go ahead with that. So here the logic is very simple. We fork, we check for error condition to see if fork failed or not, and if we are child, then we run the tracing process, otherwise we try to trace our child process. So tracy part is this. This is the code that will attach using ptrace, then it will raise this signal, and then here it will run a simple loop here. And here we are then this is a tracer part. Here we wait for the PID attached to it, and then we set certain ptrace options. We check for syscall. We only want to stop for syscall here. So when we stop for it, we capture the registers using ptrace get registers, and then we check syscall number in accumulator. And if it is same as our custom syscall here, then we basically fix this. So we are basically swapping the operands of that syscall, and then we set the registers using ptrace setrex, and then we simply continue the process, right? So its normal execution will look something like this. This is something will happen, and if we try to do this and I try to run it, here we will see something that detaching after fork. So our debugger is detaching because of fork, so we have to follow fork mode child. So in case of fork, instead of attaching to parent process, we want to go to child process instead. So we try to run it again, and here it okay, we got signal continue, so we do this, and here we got this incorrect state that our program has returned in an incorrect state. And if we do this without it, without a debugger, this particular line does not come up. Any questions so far here? Any questions?
I guess there's no question right now coming up, so we can continue.
Okay, great. So here this basically completes our preventing debugging part, and now we will move to evading from debugger part. So for evasion, we need to understand how exactly a debugger works apart from a bunch of calls to ptrace. So for debugger basics, there are something called breakpoints, and then there are two types of breakpoints. One is software breakpoints, and the one is hardware breakpoints, which is set using debug register 0 to 7, and out of which some of them are reserved. And the catch here is that these registers are accessible only in range 0. Or we can set these registers using ptrace syscall. So it will take our request, go to kernel, set the registers, come back to us. Apart from that, we have something called trace point, we have something called watch point, and these are again implemented using hardware breakpoints to figure out, for example, this watch point is used for memory, so we can set a watch point on particular address, and if contents at that address change, the debugger will alert us. Similarly, we can set an watch point for read access as well. So whenever that particular address is being read by the program, we will get an alert along with all the exact instruction which is trying to read from that particular address. Then we have something called execution control. Here we have step in, here we have, then we have step over, and we have step out. If you have used some GUI for debugger, maybe you have notice that there are certain small buttons saying step in, step over, step out. So it is like this. So step in will basically execute exactly one instruction and will follow calls, etc. Step over will execute exactly one instruction but will not follow the calls, etc. For example, if I have something like this, for example, if I have call foobar, right? So if I do step uh, in will take me to uh, foobar plus 0x0 address, as in the first instruction of foobar, right? And if I do step over, it will break after foobar returns. So this is the major difference between step in and step over. Step out is something slightly different. It will continue execution until our current function returns. So suppose if I am in foobar and I do step over, hit step over here, and my function continues to here. So my code will, as my debugger will break somewhere here, mostly after, mostly at return address after foobar. So it is like this. So when we are debugging, we can use these controls to quickly move around in the running code to see where is interesting things are happening. For example, if I want to inspect only one particular function, I can set a breakpoint there. When breakpoint hits there, I can continue execution step by step, one instruction at a time, if I want to closely monitor what is going on. And if I think that okay, I am satisfied with what I have analyzed in current function, I just want to exit from this particular function, so I will simply step out of it. Okay, and if I don't want to inspect the state by stopping the debugger again and again, what I will do that I will simply continue the execution until another breakpoint is hit. So this is basically how debugger works. And now back to breakpoint. As I told you, there are two ways. One is software breakpoint, one is hardware breakpoint. So here we are going to deal with software breakpoints, which are most easy type of breakpoints actually. So most of the debuggers that you are going to encounter, they will be using software breakpoint. Even GDB, although it has capability to set hardware breakpoint, it will use software breakpoint by default. So this is something that we can try to figure out how to detect and possibly prevent this thing. So how exactly it happens that we have machine code and assembly. For example, if I show you something here, so wait. Uh, okay, so our compiled code looks something like this. So these are assembly instructions. These are the raw machine bytes, and this is basically offset. So suppose I want to set a breakpoint at this instruction or this instruction or maybe this instruction. So here, before we do anything, we have to notice that there are instructions which are as small as 1 byte. Then there are instructions which are as big as 1, 2, 3, 4, 5, 6, 7, which are 7 bytes long. And then there are instructions which are somewhere in between. So our instructions are some where 1 to 7 bytes long, and if we are going to set a breakpoint, we have to use an interrupt. So it is the most common way to implement software breakpoint. So we have to overwrite and the instruction with our breakpoint interrupt. Now there is a problem. The problem is that for bigger instructions it is fine. We can override 2-3 bytes and it won't be end of the world. But it will be a problem with single byte instructions. For example, if I want to set breakpoint here on this first instruction and my machine code for interrupt is 2 bytes long, so I will be spilling over in the next function, and that means that if I revert it back to original code, my instruction pointer will be pointing somewhere in between of the next instruction, and it won't really work, because then the whole interpretation of machine code will change and eventually it is going to crash. That is not something we want. So what we do, that we define we define this interrupt to be single byte instruction, as in we simply, the machine code is 0xcc. Can you please explain in a little bit depth how it is ordered? Yes, we will be doing that part in code. Just hold for a moment. So the interrupt is actually interrupt third, and in machine code it is 0xcc. So if I want to set what yeah if I want to set a breakpoint somewhere, suppose here, so what I will do, that I will change its first byte to 0xcc, and before I do that I have to take a copy of this particular byte. I will save it somewhere, then I overwrite it with 0xcc, then I continue the execution, and when CPU comes to this, it will stop, it will raise an interrupt. The interrupt signal will be captured by debugger, and debugger sees that okay, it is the third interrupt that has been raised, that means our breakpoint has been hit. So what it will do, that it will go back to here, it will remove that 0xcc part, it will override this original byte here again, and then it will basically start this execution from here again. And once we are past this instruction, the debugger will set the breakpoint again unless we basically remove it. So this is how it works. So that means that we have some clue to detect breakpoint at least. So how we are going to detect breakpoint is very easy now. So suppose we have uh, some function here, like we have some function here, we have some function uh, here, and then we want to detect breakpoint at foo. So what we do, we uh, take address of foo, and it is very easy actually. In C and C++, you have to typecast function pointer to const unsigned char pointer. So once you do this, you have an address to this particular function's first byte, and using that pointer you can read the function byte by byte. Now another thing that we have to be careful here, that these will be on memory pages which will be set read and execute, but no write, as in we cannot write this part from our code unless we change the memory permission, but we can read. So for detection at least this will work. We will simply start reading from here, and there are two ways to figure out how long we have to read. One is to we can count total bytes here, or we can use nm command. Wait, let me show you nm command. command that will give size of symbol. Oh yes. So we can use this particular utility as well. So this is our offset, this is our size, and this is a symbol. Here you see the names are completely garbled up because we are using C++ and there is something called name mangling. So we can use something like this, or we can use GDB to figure out how many bytes are there, or maybe you can use something even more lazier, and that is this. We take address of foo, we take address of bar, and what we do, we start reading from first byte of foo until we hit bar and check if there is any 0xcc. So that is one way, but there is a problem that we may have this particular byte as part of another instruction. So that will be a false positive. That is an issue. 0xcc may be part of another instruction. So this becomes case of false positive. So for this, what we do that there is a mitigation. We match only first bytes of individual instructions. Now there is a question that how we figure out where exactly instruction is starting. For example, if I am using something like this, how do I figure out whether my instruction is starting here, here, or here, or maybe here? So again, this is actually very simple. What we do that we attach debugger, and what we do that we disassemble. Suppose this is the function that I want to figure out where instructions start. So I do this, and I take this part in angle brackets. So this will give me the offsets where instructions are starting. So first instruction starts at byte 0, next one at byte 1, then at byte 4, 8, 15, 20, 27, and so on. So we basically dump this and we reuse this in our code to figure out where our instructions are. Now there are various possibilities. So there are two ways an analyst is going to break into a function. First one is by using break this function command, and this will usually at beginning of function, right? So this one, for this one, we don't have to match all instructions, but if we are trying to figure out if something is breaking somewhere in between the function, then we have to match all individual instructions to figure out whether there is a breakpoint or not. So the code looks something like this. Okay, so this is the first case where we are only going to check for very beginning in the function. So this is the function where I want to check whether there is a breakpoint or not. So I typecast the pointer, and then I pass it to this function, and here I simply check whether first byte is 0xcc or not. And if it is the case, we say that we have found a breakpoint. Now this code has another little bit of issue. GDB detect breakpoint 1. What is the function name? Okay, so what we do that we bracket main run. Okay, so disassemble secret. Oh shit, Okay, so here we are. We want to set breakpoint here. So we have set a breakpoint here, and I try to run it. It says breakpoint detected, right? So okay, now we will do something little bit different. We will do a break secret, and now if you notice here, breakpoint was set on line 14. That is here in the beginning, but when I do this by function name, it is set at line 15, as in from where the loop is starting. So that means that it is not going to be on very first byte of the function. So if we do this, oh, see, we have hit the breakpoint, our check has failed. So this is a limitation. This happens because this particular binary has debugging symbols compiled with it. So compiler can see which source file and which line number correspond to which instruction. So for that, we move to next one. Wait, what is, yes. So here what we do that I have stored the offset by taking it from debugger, just like just using the trick that I just showed you some moments ago. So here what I do that I pass function address, I pass array of offsets, and then I check whether at every offset if there is a breakpoint or not. It is very similar to previous one. So here what we do, okay, let us run it before this. Okay, this works. We try to break on this, and then we try to run, and it says that the point has been detected. So we know that our code is basically working correctly. Now since we have uh, successfully detected the breakpoint, our next target is to figure out a way to remove this. So we don't have to basically go down to the debugger and analyst. So what we do that here we know that our byte is going to be replaced with 0xcc. So for that, what we do removing breakpoints. So what we do that we have copy of first bytes of all instructions, and we have offset of all instructions just like previous case. So what we do that uh, we basically iterate over instructions. If there is a breakpoint, we restore the byte, and then we continue the execution. So this is the very simple logic. Now this is the tricky part. It is tricky part because this part is not writable. So what we do that we try to make function writable. So what we do under Linux, we cannot set permission on arbitrary address. Unlike Windows, Windows allows setting permission on arbitrary addresses and on arbitrary size chunks, but on Linux, that is not how it happens. It happens on page size boundary. So it means that if I have to change permission, I have to change it on entire page. If I want to overwrite, if I want to restore permissions, I have to do it on entire page. I cannot do it into part of a page. So first step is to figure out page size then we have to figure out where our page begins. Then what we do that we set permission on we set permission on basically this range, page begin to page begin plus page size. So this will set the permission on one page. Now for this demo, I am assuming that our entire function will fit in one page, because the demo function is really small, but that is something not guaranteed. Okay, so it is possible that a function may spill over couple of pages. So you have to figure out whether your last instruction is uh, going into another page, or it is on same page. That is the check that you have to figure out, and then you have to figure out how many pages you have to change permission on. And for this we have mprotect function. So once we are done with this, we can successfully overwrite it. So this is how we do. Now one can ask whether debuggers are doing the exactly same thing when they try to overwrite it. So the answer is no. The debugger doesn't have to change memory permissions, otherwise it won't be a proper debugger, right? We're using ptrace calls. We can write at any place in our debuggy process memory without changing any permission at all. But if a process wants to overwrite parts of its own code, then that process has to change memory permissions. So this is how we do it. Wait, this is our offsets. This is our original bytes, as in these are first bytes from every instruction. Then here what we do that we check for breakpoint, and if it is there we remove breakpoint. So remove breakpoint is defined like this. This is the function address. So what we do that first we figure out size of our page, and then we figure out the starting address of our page. Then we use mprotect. This is the beginning address, total number of bytes where we want to change permission on, then the desired permissions. Here I am setting read, write, execute, and if it is not equal to 0, that means that protection has failed. So here we bail out. And then once it is done, here logic is very simple. First I check if original bytes match, and if they don't, I simply overwrite, and then I return true to signal that yes, breakpoint has been removed, just to deal with certain error cases. Here this function remains same. So if I try to run it, wait, detect breakpoint 3. So yes, this works. And if I want to, okay, so what we do that we break add secret function and we try to run it. Oops, debugger did not break on the breakpoint. It is just saying that process exited normally. Here we detected the breakpoint, we removed the breakpoint, and we continued the execution. So here what happens that analyst may keep waiting for the breakpoint to hit, but that breakpoint will basically never hit. And now there is a basically extension of this technique that when we remove a breakpoint, it is also possible that we can present a fake breakpoint by setting a breakpoint in a dummy function that we call just to confuse the analyst. So we set a breakpoint in that dummy function, we do our work, then we call that dummy function, and debugger will halt there. So that is something that we can do. And here we have done the breakpoint removal part. So okay, any questions so far before I proceed to next part?
Hello.
Hello. Yes.
Mr. Ji, there's no question. I guess not even on YouTube.
Okay. So now,
Totally agree.
okay. So once we are here, okay, we have
One
done.
second. Mr. Ji, there's one question saying, is it possible to bypass this technique for analyst with disassembly?
Yes, it is possible to bypass this by basically patching out this particular function, this one here, where I am trying to overwrite it. Here, an analyst can simply overwrite knock everywhere. So basically, this function will only check, but it will not overwrite anything. So that is one way to figure it out. And the good thing is that the next part that I am going to cover today is on how to deal with patching and how to remove the patching. Okay, so you can try to patch the function to basically remove these things, but then there are mitigations for that too. That is something that I am going to cover here. So this leads to next part, that is code patching. And code patching is very simple actually, that using debugger we try to overwrite certain instructions. Wait, instructions in memory. So this is generally used to mitigate certain things. For example, that breakpoint removal, or to basically nullify certain checks. And here, what we want to do, that we don't want an analyst to be able to patch our function. So again, there are two parts. One is patch detection. Another one is patch removal, as in unpatching. So if you try to patch it, the function will revert itself back to original state. Now here there are two ways. One is very simple. We can simply copy all the bytes, copy all original bytes of function and match it at runtime. But then there is a problem, and the problem is that the analyst will modify the function and this copy of bytes as well. So this will fail. So what we do, that we do checksum verification on the code. So instead of storing original bytes, what we do, we only calculate a checksum. We calculate the checksum, we hard code that in the binary, and then at runtime we simply match if the checksum is matching or not. So in case if someone wants to evade that, he has to figure out how exactly the checksum is getting calculated. Then he has to patch, calculate the new checksum, overwrite that, and then he will be able to bypass. So first we will cover these two techniques. So wait. Okay. So this is the first technique. Here we have all the machine code, and here what we are doing, we are checking whether the function is passed or not. So I pass function pointer and machine code. So this is function passed, and is defined something like this. I start from first byte of the function, and I continue until there are bytes in this dynamic array, and I keep matching if those bytes match or not. If they do not match, I say that function is passed. This is the very simple logic. So if we want to, okay, there is no patching detected because there is no patching. And wait, what was the function name that we were checking patching on? Oh yes, secret function. So what we do, that we get at main run, we disassemble secret. So here we get all the addresses. So here, for sake of patching, what we will do, that we will simply rearrange these three instructions. So let me override something. Wait, how do I overwrite it? Wait, I have to figure out. GDB overwrite memory. Wait, I forgot that particular command. Oh yes. So what I do, set unsigned head pointer, and I copy this. So here I do 0xC9, then next one C3, and then next one 90. So let me confirm that I didn't screw it up. Disassemble secret. Oh yes, good. So here we have nop, leave, and ret. Here we have leave, ret, and nop. So I just changed the order. And now what we do, that we will try to continue the execution. Oops. This says that function has been patched, and correctly so. Now let us try to improve this. So as improvement, what we do, we move to checksum validation, because an analyst may change this part as well. So the patching detection will not work anymore. So what we do, that we do something like this. So this is the function, and now from here to here, I have defined two functions to generate CRC32 checksum, because that is something really easy to implement. So I went with that way. So here what I am doing for patching detection, that I am taking function pointer, total machine code size, and the checksum. So here I calculate the checksum, and then I check if this is matching with original one or not. So original one is basically this. So okay, let us do it. Okay, that makes sense. There is no patching detection, and we do this. Breakpoint, run this, assemble secret. We do the exactly same thing here as well. Unsigned head pointer 0xC9. Then we do C3, and finally 90. We verify that our function has been patched. Yes, that is correct. And then we try to continue, and it says that function has been patched because our checksum validation has failed. Now here we don't have to rely on CRC32. We can generate MD5, we can generate SHA1, and if we have SHA1, then yes, again, then analyst can figure out which checksum we are actually using, and then try to override that as well. Now we have next and last part of this, and that is patching removal. And for patching removal, the idea is very simple. You have basically two copies of the function. You have two copies, one executable, one in buffer. This one can be encrypted. It can be at some remote server or somewhere else. that depends upon you. So what we do that if patching is detected, it will override function with original copy. Now this part can be turned into really difficult. For example, uh, if original copy is encrypted with private key and binary contains only public key to decrypt it. So in that case, if analyst figures out that okay, fine, I will deal with that as well. So yes, you can patch the original function, but you cannot decrypt it. We cannot encrypt it with correct key to deal with this patch removal part. Again, there are ways to modify a large part of binary to figure out to basically block a large part of operations, but then there are mitigations against that as well. So these techniques are not limited to one function. You can expand them to as many as functions you want. So here what we are going to do, that we are not going to involve in encryption. We will simply do this part, and that looks something like this. So uh, here I have the original bytes, the machine code. So instead of keeping it as plain text like I have done here, you can keep it encrypted using some key, or at some other part of binary, or in some database, some remote server, somewhere else. And here what we are doing, that we check if function is patched, and if it is so, we unpatch the function. So this function patched part is same. We are doing that checksum validation, and unpatch is again same. We are simply matching the actual bytes with original copy that we have stored, and if it is different, we are simply overwriting it. So it looks something like this. So jdbq break main run. So disassemble secret. So here again what we will do, that we will unsigned char pointer to 0xc9, and we do this here. Then we verify that it has changed. Yes, and now what we do, that we break here. Mm, we break here at line 153, detect patch cpp break detect patch. Which line was this? 153. Okay, so what we do, that we here note that we have changed the order of these instructions. So here what we are going to do, we are going to continue. Okay, function unpatching has been done, and we are going to verify that our function has been unpatched. So here we have nop, leave, and ret. Here we had leave, ret, and nop, and nop, leave, and ret was the original sequence. So our patching has been reverted back to original code, and now if I continue, it is going to work as intended. And now there is another nice side effect of this. For example, suppose if I do this and I set a breakpoint here, and then I try to run, it will say that function patching has been detected and function has been unpatched. And obviously this is the case because somewhere in the function it found 0xcc at instruction boundary, which means that the function has been modified. So it basically overwrites that original copy, thereby removing the breakpoint completely. And this is why we don't hit the breakpoint and process terminates normally, and debugger says that okay, process has terminated. So yes, this is for today. Now, does anyone have any questions for what we have covered today?
There's one question asking how to create malware. Can you please give overview?
Bro, you can go with previous parts of videos that have been uploaded on our website and YouTube both. Part of it has been covered, part of it will be covered in future sessions. I recommend you start from the first video that was on keyloggers. So from keyloggers we have started and we are here today. Dhwani, can you please share the link with him?
Yeah, I'll share the link with him.
Okay, thank you.
Abneesh Kumar.
Any more questions? Anyone?
अरे मिश्रा जी आपके लिए क्वेश्चन आया. What terminal you are using?
क्या?
आपका टर्मिनल कौन सा है?
मेरा कर्नल कौन सा?
टर्मिनल जो यूज कर रहे हो ना.
This is console from KDE, and this particular shell is Z shell with oh my ZSH and custom theme. This particular theme is custom one.
तो ऐसे सब क्वेश्चन पूछेंगे लोग अब.
क्या बात है.
चलो
तो मेरे ख्याल से अब इसे रैप अप करना चाहिए.
हाँ ठीक है.
ठीक.
वनी दीदी.
हाँ बोलो. हेलो.
आपकी आवाज कट रही है. कहाँ हो दीदी?
अरे भाई रुको.
क्या हो गया?
ये अवनेश कुमार को उस पर सीरीज का लिंक ही नहीं मिला. रुको 1 मिनट.
अरे भेजा तो सही चैट पे उनको aristry.live भेजा ना.
हाँ, तो वो उस पार्टिकुलर वेब पेज पे नहीं होगा. मैंने पूरा वो ये malware वाले पेज का ही लिंक दे दिया.
FWM वाले पे वो सारा कुछ. demigod.html वाले पे. दीदी बताओ वो हिमांशु वाला क्या सीन है?
Meanings है से expert writing Windows expert writing with Windows with reverse engineering. Would be interested है candidate to speak us share the details of and they can register with सुनाई दे.
ध्वनि आवाज बहुत कट रही है.
एक सेकंड को मैं ये बोल रही हूँ हिमांशु का there are like paid courses of Himanshu is paid for expert.
Okay, so how many people here have interest in learning about malware? Expert development. Anyone who want to learn explore development from basic, not
Yes,
basic.
we can drop them a mail and the interested candidates can revert to us.
Yes, a master course is live yesterday, so you can go and have it from there. And we are having some exclusive coupons on that, so stay tuned with us as he is going to explain what he have over there and give you some, discounted coupon because you're part of our community. So stay tuned, join for his talk, the upcoming talk, and you can see what's going on. Okay, so that will be there. And there are other few courses that we are thinking of making it as a paid and making it available offline and online as a classroom training, not recorded sessions. So if you're interested on like any of these kind of stuff, let us know and we can make sure that whatever you need, we have this is covered. So you got any questions, any feedbacks, any suggestions, you can write me on hello@aristi.com. Sorry, not com, dot live. We are not using .com. Okay, feel free. And that's all we have for today. And for next sessions, we have networking tomorrow. That will be the basic of networking, OSI model, how you can design your own networks in application, might be a packet tracer or something. So that will be taken care by Chandresh Gupta, and he will be available tomorrow. If you want to know about networking, feel free to join us tomorrow and we can talk about all those things. All right, so how the session? You're liking it?
Guys, please share your feedbacks because I seriously don't know whether you are enjoying this course or you are getting too much difficulty somewhere, or
Yes.
you want me to change something, or you want me to focus more on certain specific topics. At least send some feedback, right?
Yeah.
Otherwise we will be like, okay, yeah, we are not getting any feedback, so we will keep continuing what we are doing in the same fashion we are doing right now.
So make sure you are providing us feedback, so that will easy for us. Okay, you don't have feedback link. Wait. This is the feedback link. You can go and follow up. I can just put as bit.ly. Again, this is the link that we used last time. Yeah, you can push it on bit.ly.
Animesh,
Crypto development. Can you please take session on crypto development, Mishra ji?
हाँ भाई,
Crypto development.
क्रिप्टो डेवलपमेंट है जी,
Cryptor.
क्रिप्टर वो तो पार्ट निकल चुका है भाई। खैर चलो, एक मिनट, किसने भेजा है वो तो चलो मैं आगे वापस कवर करूंगा। अभी स्टैटिक एनालिसिस वाला पार्ट भी आएगा, अभी तो डायनामिक एनालिसिस की टेक्निक्स चल रही हैं, स्टैटिक का भी पार्ट आएगा, तो स्टैटिक वाले में मैं वापस स्क्रिप्टर पैकर वगैरह थोड़ा सा रिविजिट करूंगा।
Of malware with Windows 2. For Windows, just have a look on our YouTube channel. There is a playlist for Windows exploitation.
नहीं वो भाई विंडोज का मैलवेयर पे चाहिए, एक्सप्लॉयटेशन पे नहीं। विंडोज मैलवेयर का हिसाब थोड़ा सा एक्सप्लॉयटेशन से अलग है, वो भी करेंगे, लेकिन अभी लाइनक्स वाला थोड़ा सा खत्म हो जाए फिर विंडोज वाले पे फोकस करते हैं। एक्चुअली बहुत सारे टेक्निक्स हैं जो दोनों जगह एक जैसा मैप होंगी, भी जैसा डिबगर वाला है तो वो दोनों जगह एक जैसा मैप होगा। पैचिंग का है वो भी दोनों जगह एक जैसा चलेगा, ठीक है, लेकिन जो कीलॉगर है, कीलॉगर का हिसाब बदल जाएगा, हुकिंग का हिसाब बदल जाएगा। तो जहाँ जहाँ पे चेंज है वो उसका फिर मेलवेयर का विंडोज स्पेसिफिक एक छोटा सा सीरीज रखेंगे, लेकिन अभी पहले लाइनक्स का खत्म हो जाए।
तो कवर सब करेंगे, थोड़ा वेट कर लो भाई।
हाँ, क्योंकि भाई बैंडविड्थ कम है।
Okay, now anyone here want to take sessions? Yeah, like you're more than welcome to send me an email. Like you already have 3 speakers, having more is always a good idea. Okay. Nope. Guys, please do a favor, send a feedback, so that will help us. Okay, and yeah, that's all for today. We'll see you guys next time then. क्या बोलते हो? अरे यार, अभी तक तो फीडबैक नहीं आया सर। चलो ठीक है। चलो इसके बाद मैं देखता हूँ। ओके, थैंक यू गाइस फॉर जॉइनिंग अस फॉर टुडे एंड विल सी यू टुमारो। ओके, सो मिश्रा जी सेशन एंड कर रहे हैं।
हाँ ठीक है, थैंक यू एवरीवन।
थैंक यू एवरीवन फॉर जॉइनिंग इन।
और